So in part 3 of section 6.7, we're going to tackle example 7. Now, example 7 asks us how long it's going to take 5,000 to double if it's invested at 9.25% compounded, but then we have to do this multiple times, annually, semi-annually, monthly, daily, and then continuously. So again, a reminder, this is our formula, A equals PE. Sorry, that's not our formula. Now for the first 4 parts. For the first 4 parts, it's talking about annually, semi-annually, monthly, daily, and so forth. So that's telling me to use the compound interest formula. And what they're asking us to find is time. So what we could do is plug in the first set of numbers and then solve it algebraically for time. Plug in the second set of numbers, solve it algebraically for time. Same thing for part C and part D. However, because we're going to be doing the same process multiple times, why not just take the formula and solve the formula for time first? So we're going to create our own formula and then we can just plug and shove on those parts. So we want to solve for T. We can do this. We're capable. So the first thing we're going to do is the same thing we did in the previous example. We're going to divide this P out of there. So that'll give me A divided by P is equal to 1 plus R over N to the NT. But because we're solving for time and time is stuck there, if there is an exponent, we're going to take the log of both sides. I'll still use ln just because it's quicker to write. So I have the natural log of A divided by P is equal to the natural log of 1 plus R over N to the NT. Again, the reason we're doing that is that now lets me move the NT out in front of that logarithm. So I have N times T times the natural log of 1 plus Rn equals the natural log of A divided by P. Solving for T, so believe it or not, we're going to divide by everything else. We're going to divide by the N and also the natural log of that quantity, all in the same step, because that's going to get rid of that, and that's going to leave T all by itself. So we're dividing by this. And that was it. We're done. It didn't take us very long. So we have a new formula. So our formula says that the time is equal to the natural log of the amount divided by the principal, all over N times the natural log of 1 plus R over N. Now we can come in and use that formula. So there's our new formula that we're going to use to figure out how long it's going to take our money to double. It's kind of slick to be able to solve for formulas. Okay. So in this particular problem, we're trying to double $10,000. So as a comment, the amount at the end of time is, it's 5,000 we're doubling. So the amount at the end of the time would be 10,000. P would be equal to 5,000. And because our formula has A over P, you can see that A divided by P is going to be 2. And that's that doubling. So if I were going to try and triple that, this would end up being a 3. So it's kind of nice that it's constant for us. Our interest rate in this case is 9.25%. So that would be 0.0925. So I think I have everything. So for part A, excuse me, I'm froggy this morning. It's saying annually. So when we do annually, we know N is equal to 1. So now we're just going to use our formula. So T is going to be equal to the natural log of 2. That's our A divided by P, all over N times, N is 1. We're replacing N. We know N is 1. So 1 times the natural log of 1 plus R, which was the 0.0925, all over 1. And there it is. So there's our formula. So we've used our formula. Now you need to take it to your calculator. Again, make sure that you're closing any parentheses, and to get into a habit when you do multiple steps in the denominator, putting the entire denominator in a set of parentheses. And if you do that, you should end up with 7.8. And that would be. So if I have compounded annually at 9.25%, it's going to take 7.83 years for my money to double. Okay. Part B says, okay, what if instead we're doing it semi-annual? The only thing that changes here is N. So now N is equal to 2. Still got our formula. So T is going to be equal to the natural log of 2. That's the A over P still. But now we're going to have 2 times the natural log of 1 plus 0.0925 divided by 2. So that's why you need parentheses around the entire denominator, because you now have got some things more interesting than those ones in the previous example. Number crunching that through, you're going to find out that it's going to take 7.67 years. So not a whole lot less in terms of time, but you're only compounding it one more time during that time period. So one more time each year during that 7.67 years. Okay, well, what if we go one more time and do it in terms of monthly? So part C says monthly. And monthly tells us that n is equal to 12. So we'll have t equals the natural log of 2, still doing the same thing there. But now we're going to have 12 times the natural log of 1 plus 0.0925 divided by 12. See how convenient this is that we wrote our own formula, or algebraically found our own formula that we can just plug into each time. Otherwise, we'd have to rearrange this every single time in order to find t. And if you do this one and number crunch it through, I ended up with 7.494. I'm going to carry one more digit here and you'll see why. Years. That was part C. And finally on part D, it says, okay, what about daily? So if we're going to do daily, then we now know n is 365. So my 12s are going to change to 365s. If you're using the graphing calculator, you can use the second enter feature, which retypes the whole line for you. And then go back and insert where there's a 12, the 365. So that would also work. 365 times the natural log of 1 plus 0.0925 divided by 365. I guess you could also build a table now that I'm thinking about it, right? Where the input value is the daily, the n, right? So this would be your x basically, and y would be that function at the end. And just build a table. That would work too. That'd be really convenient. And if we do daily, you end up with I'm messing up on my answers here. So the monthly came out to be, you're probably screaming at me because you never crunched it through on your calculator. The monthly came out to be 7.52. The daily is the 7.49 years. Okay. So let's just double check to make sure I've got them all right. I'm done with the formula because the next part's different. So let's summarize where we're at so far. So far, this is what we know. Yes, switch to a marker that I think is a little bit stronger. So when we did n equals 1, that was the annually, we ended up with 7.83 years. When we did n equals 2 for semi-annually, we should have had 7.67 years. When n equals monthly, that was the 12 for n, that was 7.52 years. And n equals 365 came out to be the 7.494. So you can see that each time we increase the compounding period, we definitely are having to invest it for a lesser amount of time. But again, we're talking days here. We're not talking huge amounts of time. And again, part of that's because we're only doing doubling and we're at only, 9.25%. So that's why we're not seeing big numbers. But part E is now asking us to come in and increase the compounding past daily, which is continuously. So for part E, we have to switch formulas. Part E says, what if we do continuously? And because I like to bring algebra into play anytime we can do this, instead of just plugging the numbers in, let's go solve this formula for time. So we would still take A and divide it by P. That's going to be equal to E to the RT. You'd come in and take the natural log. So A divided by P is equal to RT natural log of B. Notice this time I just went ahead and moved the RT out front. This we know is equal to 1. So we'd end up dividing by R. So our new formula using the continuous interest would be the natural log of A divided by P all over R. So for our specific example, we know that A divided by P is still 2. We're doubling our money, 10,000 divided by 5,000. The interest rate was the 0.0925. That's a lot nicer as a formula to work with. And if you do that, you end up with 7.493. So when we used continuous, we ended up with 7.493 years. So everybody thinks that continuous interest sounds so amazing because they're going to do it more often than daily. But notice it is really only gaining us a little, what, half a day, maybe, if that. I'd have to multiply by 365 to see what the actual difference is. Right? So, and that wraps up the money formulas, so compound interest in our textbook. And our final section, which is section 6.8, now takes and does exponential growth and decay over in the science world. So in the sciences, biology, chemistry, those kinds of things. And that'll be our final section. So we're almost there. Thank you.